Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuits. In our previous interactions, we have actually seen the functioning of BJT, various modes of operation of a bipolar transistor, and then we have seen BJT as an amplifier, right. So, given a small input signal, how can I actually achieve amplification in a voltage domain as well as in current domain, of course. We have seen that in our previous discussion. We have also seen the three modes of operation of BJT, which is common emitter, common base and common collector, and we have appreciated what is the utility of these three modes of operation of bipolar transistor. What we will be doing the last part of bipolar before we move to CMOS technology is look to BJT as an inverter, because that is the basic logic which we try to design initially. So, we will look at BJT inverter and then we will look into the various second order effects of an inverter, right, second order effects of bipolar transistors, right. One we have already dealt earlier, but in details we will be dealing it now. One is the early effect, but before we move ahead with that, let me first discuss with you a simple BJT inverter, right. So, the topic of this slide, the topic of this section is basically your BJT, simple BJT inverter and second order effects, right. So, this is the topic of the this lecture series talk. So, what we will be covering here? We will be covering basic simple BJT inverter. So, given a BJT inverter, can we find out the inverter characteristics of a BJT and use it for logic inversion purposes? That is what we will be seeing here. Maybe we will solve a numerical example in this case. I will show you a numerical example, right, numerical example, and we will also concentrate on what are known as noise margins for BJT, right. So, we will also discuss this in detail when we go to CMOS logic, but for BJT logic we will also understand what is noise margin and how do you define noise margin in a BJT, and this will be through a numerical example set up here. Then subsequently we will be going for other second order effects of BJT, where we will be looking at base widening, then we will be looking at early effect and so on and so forth, and then how does it influence therefore the IV characteristics of a BJT, right. That will take care of approximately the major understanding portion of BJT, and therefore knowing this you can actually approach BJT from analog point of view when you use it as an amplifier, and you can also approach it from digital point of view when you use it as a inverter, right. So, this is the what we will be. So, that is the reason or the logic for having this bipolar transistor as the first part of this new lecture series on NPTEL. With the knowledge we have gained now, let me just show you a simple BJT inverter. As you can see, the simple BJT inverter is this which you can see here, and this is a BJT which is NPN transistor. So, I have an NPN transistor here whose emitter is grounded. So, this is basically an emitter grounded inverter, and we apply a voltage input to the base through a base resistance RB, and we try to extract the output voltage from the collector of the BJT, and you apply a voltage VCC which is equals to 5 volts here, right. So, this is the basic principle we have already seen earlier. Now, we will look into details from the voltage transfer characteristics point of view. So, as you can see, therefore, when your input is typically very low, right, it is much smaller than 0.1, then we can when Vi is much smaller than 0.7 volts, which is the turn on voltage for this base emitter junction, right. You would expect to see that this is cut off, NPN will be in cut off, and as a result what will happen is that this VO will be exactly equals to 5 volts, right. Why? Because if we had discussed this earlier also, that we can write down VCC to be equals to ICRC plus VCE, right. This is VCE, this one is VCE, right, and this is IC is flowing, let us suppose here. So, IC, so ICRC is the voltage drop across this resistor, this is ICRC, this voltage drop plus this voltage drop must be equals to VCC. Now, you see, since your emitter is not through a resistor, it is directly coupled to the ground, VCE can also be written as simply VC. So, VCE is nothing but the collector your VE, I am sorry, VE, right, VCE can be exactly written as VC, because VE is actually equals to 0, right, because the emitter is grounded. But keeping this in mind, therefore, when your device is in the cutoff state, when this is cut off, NPN is cut off, IC is equals to 0. IC equals to 0 implies that your VCC is equals to VCE, right, because IC equals to 0 means this is 0, and therefore VCC equals to ICE, right. And therefore, you can safely assume that what you can see from all this discussion is that if you try to find out the value of V out will be equals to, will be nothing but this VCE, right. V out is equals to VCC, right. Now, when my IC equals to 0, right, VCC equals to ICRC plus VCE, when my IC equals to 0, this goes off, right, and therefore, the voltage across this thing is pretty large, right, it is pretty large, because all the voltage drop will be across this. So, this is cut off, sorry. So, this is cut off, and therefore, I will get V0 to be equals to a high value equals to VCC, right, and you get a large value here. So, when the device is in the cutoff mode, your voltages are all going to 0, and as a result what will happen is that when your device is in cutoff mode, right, IC equals to 0, implying that your output voltage is approximately equals to VCC. So, if you are using a plus 5 volt VCC, I will get this to be as equals to plus 5 volts, right, plus VCC, right. Now, as you go on increasing the value of Vi from a low value to a high value, you switch on the device drastically, and when you switch it on, what happens is that this becomes from cutoff to cutoff off to it goes to saturation. Why saturation? Because the voltages are not large enough in order to ensure that these have moved to fully into on. When it moves to cutoff, this VCE can be written as VCE saturated VC, which is approximately equals to 0.2 volts, which means that this is the value of voltage which you get as 0.2 volts at V out equals to 0.2. So, we have understood one basic fundamental principle, that whenever my input voltage is low, my output voltage is high, and vice versa. So, I can use it as an inverter. As we have also discussed in an earlier part, that below VB, so you see this if you look at this curve, and this is Vi versus Vo. So, this is basically your voltage transfer characteristics, right. This is known as VTC or characteristics, and this is known as voltage transfer characteristics, voltage transfer also referred to as VTC, right. So, if you look at the VTC, right, it is just behaving like an inverter, because when your input is VBE on till that much point, your device is cut off and the voltage is latched to VCC. Beyond VBE on, the device switches and the voltage starts to fall down, and it falls down to how much value? Equals to VCE sat, and in this region VCE sat. After this, if you even increase the value of Vi, it does not affect because the device is fully on. So, you see this region is defined as my active region, and this region is defined as my saturation region, right. So, I have got cutoff region, active region and saturation region. The active region is a region where the voltage V0 is a function of Vi, and therefore, there is a finite AV or the voltage gain, because AV will be defined as del V0 del Vi. Therefore, I will have a finite gain at the active region, right, but I will have AV equals to 0 at cutoff and saturation. At these two places my voltage gain will be 0. So, if you want to bias my device as an amplifier, you bias it in the active region of the device. If you want to bias it as a switch, then make your active region as small as possible and try to shift from cutoff from here to here, right, and you can get a digital 1 and digital 0 in the output and input side, right. So, basic BJT, therefore, we had a problem that the BJT is, though it is pretty fast in terms of switching, but the problem is that it has got a high power dissipation because of high leakages. Not only that, BJT also has a problem that to move it from saturation to cutoff, right, you have to actually remove large number of charge carriers from the saturation region, right, to make it to go into cutoff. So there is some dead time also associated with the BJT switching action, which means that the BJT has to wait minimum amount of that much amount of time before it crosses from saturation to cutoff, right, and therefore the speeds are relatively low for BJT when it acts as a switch, right. So the maximum frequency of operations are relatively low in this case as compared to the previous cases and as compared to CMOS technologies per se. So as you can see here, therefore if I want to therefore make my transistor work in the saturation region the active region, then try to make the active region as large as possible, and then this is my active region, right, and this is my active region, and this is my saturation, and this is my active, right, and this is cutoff, fine, and this is VO versus VI. Now if you want to reduce the active region, you need to bring these 2 points close to each other, which means that if I want to reduce it is something like this, right. So your active region has drastically reduced here. So the gain which you get is that your cutoff region is now very large and your saturation region is also very large, because if you remember this will be actually plus VCC, this point is plus VCC, output will be equals to plus VCC approximately if your input is equals to 0. So when your input, so when Vi equals to 0, V out will be equals to plus VCC, and that is what is written here, and when Vi equals to plus VCC, VO will be equals to 0, approximately equals to 0. So at this point when it is plus VCC, when Vi equals to plus VCC, suppose let us suppose here plus VCC, then output actually falls to 0 value or very close to 0 value, typically equals to VCE sat actually, which is approximately equals to 0.2 volts, fine. So we have learned one important point that though BJT is a good thing, but good switching action, but the point is that it cannot go below VCE sat in the lower dimension, and the highest one it will of course go to VCC. So the swing is restricted between VCC and VCE sat. This is the output swing of a bipolar junction transistor, right. So this is what you have learned, what we have learned here. We will define some important terms here, and that will be making it much easier for you to understand or appreciate that. Let us suppose I have got a curve like this, and I give like this, and then I go like this, and then we go like this, right. So we draw this curve, remember VBE on, and then we get this, and then we get this, and we of course get this into consideration. We define this to be as VOH. So this point is VOH is VOH implies output high, right, and this is VOL. So VOL is output low. So VOH is output high and VOL is output low. In our case VOH is equals to plus VCC and VOL is equals to plus VCE sat, approximately therefore equals to 0.2 volts, fine. Is it okay? We also define two terms in the input side, because this is Vi and this is Vo on the input side, and this is when VIH and VIL. It is VIL, this is VIL, this is VIL, right, VIL, and this is VIH. So VIL and VIH, why? Because when VIL means VIL is meaning that it is input is low, and VIH is meaning that input is high. So I get 4 conditions or 4 biases: VOH, VOL, VI. So I get VOH, right, VOH, VOL, VIL and VIH. VIL and VIH are input high, input low. Input low primarily means that is the maximum value, right, of your input in the low condition when the output will be actually registered as 1, and VIH is the maximum or the minimum value in the highest condition when the output will be read as 0, right. So, that you have to be very careful about what is the meaning of VIL and VIH. So, VIL is input low means this is the maximum value of input at which you will actually get a high. If you exceed this value of VIL, your output will start to drop down, and that is what is happening here, see, right. Similarly, VIH is the minimum value at which your output will be low. After this, if you look very carefully, it might fall down or it might remain constant, right. So, this is what you learned. So, typically it is 0.2 for a silicon diode, we see sat is equal to 0.2. We define a new term here, and that is how you define your we define this to be as a noise margin, and that is basically my noise margin, static noise margin we define, high noise margin is defined as VOH minus VIH, and NML is VIL minus VOL, right, VIL minus VOL. So, the difference between the voltage of VOH here and VIH here is defined as my high noise margin. So, this is defined as high noise margin, and this is referred to as a low noise margin. What does a high and low noise margin mean? This means that we will discuss also when we go to CMOS, but make it clear as well, so that we can come over it. High noise margin means that, let us suppose you have a 1 being entered into the BJT. So, my input is 1, right. Now, let us suppose there is a noise in the system, right. If the noise becomes very large, a 1 can be actually seen as a 0 by the input side, right, or it can change from 1 to 0. So, which means that, let us suppose you had biased your device somewhere here, right, and your input cycle was slightly like this, no problem. So, what is happening? The maximum value of the Q point goes here to here, no problem, your still output is high. But if you make your input very large because of noise or some other means, this Q point will shift from here to somewhere here, and therefore, the output starts to fall down, and therefore, you are not able to store an information of 1 in the output size, because the input is actually going from high to low, right. So, you had low to high. So, you had an input which was low, right, you add noise to it, right, and the maximum noise which can be added to the signal, right, without changing the output is defined as my noise margin. So, we define the high noise margin for 1 and we define low noise margin for 0, fine. So, higher this value, better your design is, because better it will be rejecting the noise. So, if your noise margin is typically say 1.5 volt, it means that till 1.5 volt you give me any data, it will be always read as output 1, right. And if the NML is also very high, it means that you give me a value of input data equal to the NML value, and it will be read as output 0. So, we have 2 noise margins, therefore, as I discussed with you, we have got a high noise margin and we have got a low noise margin, right, and we try to keep both the noise margin as high as possible. So, if you want to use it for the purpose of digital logic, then you keep your noise margins relatively high, right, you might keep this relatively high. If you want to use it as an amplifier, then keep this low, but increase the value of your, so this is your VCC, increase the value of this transition active region, then I can use it in a analog domain. But if you want to use in digital domain, keep this one as low as possible and try to achieve equal values of input and output noise margins. I will take up an example and show to you how I can follow a noise margin. Say I have got I'll give you a basic fundamental principle. I have got RC here, right, I have got resistance here, and I have got RB here, and applying an input signal. It has already been biased by a DC bias. This is RB RC and this is V plus VCC, right, and this is a transistor beta whose beta is exactly equals to, let us suppose the beta value for this is exactly equals to 50, let us suppose VCC is equals to 5 volts, RC is approximately equals to 1 kilo ohm, and RB equals to let us suppose is 10 kilo ohms. So, let us see how does my noise margin and all these things come out. So, if you see Vi is equals to VOL equals to VCE sat equals to 0.2 volts. So, when you apply Vi input, right, and I assume my output to be low. So, my input is high, my output is low, equal to VCE sat equals to 0.2, right. Similarly, when I apply VOH, input is high, right. So, in this case input is high, in this case input is low, and then I get VOH equals to VCC equals to 5 volts, right. So, when your input is low, your output is VOH, and that is almost equals to VCC, and when your input is high, output is low, almost equals to VCE sat. So, the swing is from 5 to 0.2 volts. This is the swing in the voltage domain which you see when you have a such type of system available with you. Now, assume, let us do one thing, that I assume that my V in or input is between VIL input low as well as between VIH, right. So, I am in the active region of operation. So, in the active region I can safely write down AV to be equals to V0 by Vi, output voltage by input voltage, which is minus beta times RC by RB plus R pi. We will discuss this time and again, but you can understand RC by RB is the ratio of the collector current to the base current, right. So, it is the ratio of the collector current to the base current. Beta is equals to IC by IB. So, if you multiply it, I get a voltage gain AV, right, and because beta is basically output current by input current, right. If you multiply this with RC and if you this you multiply with RB, I get output voltage upon input voltage, which is exactly equals to AV value, fine, is it okay. So, with this concept, if you put the value of RC as 1 kilo ohm, RB as 10 kilo ohm, and you also put beta to be equals to 50, I get AV to be approximately equals to minus 5 volts per volts, right, which means that it is basically negative, because obviously you are entering into a negative 180 degree phase shifted. Output is always 180 degree phase shifted with respect to input, and therefore, you get AV equals to minus 5 volt by 5 volt, right. Now, within the active region, therefore, within the active region I get AV equals to this much. Now, at when your Vi is equals to VIH, because that is what you will get, I will enter into saturation region, and I can safely write down IB to be equals to VCC minus VCE sat, right, divided by beta divided by RC, because if there would not have been beta, then it should have been IC, but you put a beta here and then directly convert into IB. So, if you solve it, I get IB to be approximately equals to 0.096 milliamps. So, it is order of microampere, right. Now, if I can write down VIH, right, equals to IBRB, IBRB is IB times RB plus VB, means this voltage which is VIH, let us suppose DC bias, is exactly equals to the voltage here and the voltage this one. So, if you add these two together, I should get the third voltage, and therefore, I get VIH equals to IBRB plus VBE, right, IBRB plus VBE. Put the value of IBRB and VBE, I get 1.66 volts. So, input high is 1.66, which we follow, right. Now, if this is true, I can write down VIH therefore to be equals to 6.66 or 1.66 volts, 1.66 volts, right. So, therefore, Vi equals to VOH equals to 5 volt, right, and VO will be equals to VCE sat, and that is equals to 0.2 volts, fine. So, I get these many definitions available to me, right. Now, if I assume these definitions are equal, then from here I can get the value of beta is the current gain, to be exactly equals to VCC minus VCE sat, right, divided by VCC minus VBE or VOH minus VBE, this divided by RC, this divided by RB, if they are exactly equal, beta will be equals to 1, right, and that is what you get, but in clearly this is equals to 11 which you get. Therefore, NMH will be equals to VOH minus VIH, and this comes out to be 5 minus 1.666, and that is equals to 3.34. In the second case, when I find NML, it is VIL minus VOL. So, what is the value of VIL? 0.7 volts minus 0.2 volts, and that is equals to 0.5 volts, right. So, we end up having a very interesting discussion on bipolar transistor, that if you do not do any manipulation in terms of doping or circuit changes, you would expect to see beta to be approximately order of 10 to 15. Once you have that beta value, you can achieve a current gain of approximately 10 to 15 within the chip, right, or within the design which you have made. So, let me find out NMH NML, and that comes out to be 3.34, and if you find out NML, it is VIL minus VOL. So, VIL is 0.7 minus 0.2, and this is 0.5 volts. So, but you see your NMH, right, is not equals to L, which means that there is a problem. That means high to low noise margin is not equals to low noise margin, which means that 1 can be transmitted very easily even with a noise figure of very high noise figure, whereas a 0 will be stopped or inverted if my output noise is typically small. So, in reality we should have NMH equals to NML, but in practical sense, as you can see in this bipolar transistor, NML is not equals to NMH, right, and that is the problem area which people face as far as designing is concerned. So, somehow or other you have to make NML equals to NMH, right, and that is what is very important, right. Okay. So, with this knowledge or with this basic criteria, we have therefore understood the basic concept of a simple BJT inverter, how does it work and what are the various features of BJT inverter. Therefore, as I discussed with you, if the inverter Vi is approximately 0 volt input, the transistor is cut off and the output voltage V0 is high and equals to VCC. So, when your input is low, output is high. Now, if the input is high and equal to VCC, the transistor can be driven into saturation, in which case the output is low and equals to VCZ. So, the output is either equals to VCC or equals to VCE sat, right, two extremes which is available for this particular design, right, and you can actually switch from one to another very fast in this case, right. Now, if you therefore see so that takes care of our understanding of this your transistor action, and you can therefore see when input is equals to 0, the output is equals to plus VCC, when the input voltage is plus VCC, the output voltage is VCE sat, right, also known as saturated collector to emitter voltage, right. So, we will do the subsequent talks in the next turn. We will look into the second order effects in a detailed manner in the next turn, and we will go into details of each one of them as we move along. So, what we have learned, BJT is an inverter, what is the noise margin, how we calculated the noise margin from the device characteristics, and how noise margin is related to the overall sensitivity and robustness of the inverter design, right. With these words, thank you very much for your patient hearing. Thank you.